So enzymes, huh? So in this particular topic, we are going to discuss regarding the properties of the enzymes and the Michaelis-Menten kinetics. Okay, these are two things that we are going to discuss here. First, enzymes, enzymatic properties. First thing is that all enzymes are proteins, but not all proteins are enzymes. So what I'm saying here is that all proteins are not enzymes because some of the proteins act as a signaling molecule or act as a receptor or act in cell signaling. Okay, so that's why saying this particular line. And the second thing is that one exception is ribozyme. Ribozyme is not a protein. Ribozyme basically made up of RNA. And ribozyme basically degrade the RNA and act in splicing mechanism which occurs post-transcriptionally. The third property of enzymes is that enzymes increase the rate of reaction. The rate of reaction without affecting the equilibrium. Do you know, Avni, what is equilibrium? Hmm?
Yes, sir.
What is equilibrium?
So where delta G is zero, delta G
When
naught is
delta
zero.
G is zero, and another thing is that after equilibrium, there is no net change in the concentration of either the substrate or the product. Okay, whether it is the reversible reaction or whether it is an irreversible reaction. Huh? So equilibrium is not going to be affected. It means that equilibrium constant is also not changed by enzyme. It means equilibrium constant remain same. Whether you add enzyme or whether you don't add enzyme, it is going to remain the same. Okay. How enzymes are going to increase the rate of the reaction? Uh, that is by lowering the activation energy. Okay. So enzymes increase the rate of reaction by decreasing or lowering the activation energy. The activation energy. So these are some of the properties of enzymes you need to remember because all of these properties are very important because most of the questions are going to come from this part, and these last two properties are most important. Lowering of the activation energy as well as the increase in the rate of the reaction, which is also known as the velocity. Okay, rate of the reaction is also known as the velocity, which is represented by V. Is that clear to you,
Yes,
Avni?
sir. Yes,
Okay,
sir.
fine, fine. Sure. Now try to understand this graph in which on y-axis we have the free energy, which is represented by G, Gibbs free energy, and on x-axis we have the reaction coordinates. And I'm going to make two graphs here. One is going to represent without enzyme, and one is going to represent with enzyme by the addition of enzyme. So first one is this. You need to remember that here we will have the substrate and here we will have the product. Hmm? So first thing I need to be clear is that here we will have the Gibbs free energy of the substrate. That is also known as the ground state free energy of the substrate. And here we will have the ground state free energy of the product. So can you tell me which energy is higher and which energy is lower in this graph?
Straight, he gives energy
Substrate
is higher.
substrate have the higher energy as compared to the product
Yes,
now. Okay.
product.
Now we are going to calculate the delta G for this particular reaction because substrate is getting converted into the product. Okay. So final is product, initial is the substrate. So we are going to have GP minus GS. So from this, you can see that delta G will be written now, because this free energy is higher than the ground state free energy of the product now. No,
Yes, sir. Yes, sir.
and delta G is negative. It means the reaction is
Spontaneous.
spontaneous. See, let me give you another example. Suppose we will have not like this, like this. Suppose here we have the substrate, here we have the product. So this reaction is going to be spontaneous in the forward direction or the backward direction? Tell me.
So non-spontaneous.
Yeah, in forward direction, this reaction will be non-spontaneous. Okay.
Yes.
In backward direction, it will be spontaneous. So any enzyme can catalyze this reaction in the backward direction, but not in the forward direction.
Forward.
Okay. Okay.
Yes, sir.
Fine. Let me remove that. Another thing is activation energy. So you can see that this amount, which I outlined here, this amount is called activation energy, which is represented by EA. Okay.
Yes, sir.
So what will be the definition of activation energy? Activation energy is the amount of energy which is required by the substrate to reach the transition state. So here we will have the transition state. Oh,
Yes, sir.
now this graph is representing the uncatalyzed reaction. Uncatalyzed reaction means we have not added the enzyme. Uncatalyzed reaction. Another graph I'm going to make here like this. So that is going to represent the enzyme catalyzed reaction. Enzyme catalyzed reaction. So you can see clearly what enzyme did here.
Yes, sir.
Enzyme have decreased the activation energy.
Activation energy. Yes, sir.
Okay. So that's why the rate of the reaction have been increased. But you need to remember that even the addition of the enzyme have not changed the ground state free energies of either the substrate or the product now.
Yes, sir.
So you can write down here no change. What enzyme do not change? What properties are not changed by enzyme by the addition of the enzyme is delta G or GS or GP. Okay.
Yes, sir.
But they decrease activation energy and increase the rate of reaction. Rate of reaction. Okay. Have you made the graph?
Yes, sir.
Okay, fine. Okay. Another thing, I like you to consider the Arrhenius equation, which is basically this is the rate constant because you need to remember uh, if I say a reaction occurs like this A to B, and here we will have the forward rate constant and we have the backward rate constant, backward reaction rate constant. So in this case, the basically the forward rate of reaction will be determined by K1 and to the concentration of a reactant. In the similar fashion, the backward reaction rate will be determined like this K minus 1, which is the backward reaction rate constant and the concentration of B. Hmm?
Yes.
So basically these are rate constants. Rate constants. From here, you can see clearly that rate is directly proportional to the rate constant. Higher is the amount of rate constant, higher will be the rate.
Yes.
Hmm? Okay. So the Arrhenius equation K is equal to A e to power minus EA upon RT. This is basically Arrhenius equation and this is the Arrhenius constant. Arrhenius constant. And this is rate constant, this is activation energy, this is gas constant, this is the absolute temperature. Okay.
Yes.
So if there is a decrease in activation energy, it means increase in rate constant. Hmm? From this logarithmic equation, you can relate that if the amount of activation energy is going to get lowered, then the rate constant is going to get increased. Note it down.
Yes.
So, till now, what enzyme changes? So, they lower down the activation energy. They
Yes.
increase the rate of the reaction, which I'm representing with V or velocity. They increase the
Yes,
rate
sir.
of the reaction. How they increase the rate of the reaction? By increasing the rate constant. Because there is a inverse relation between the activation energy and the rate constant.
Yes, sir. Yes.
What they do not change, delta G, ground state free energy of the substrate and ground state free energy of the product.
Product.
Okay. And equilibrium constant. No,
Yes, sir. Yes.
do not affect the equilibrium. Do not affect the equilibrium. Okay, is it done?
Yes, sir.
Fine. Now, let me come to the derivation of Michaelis-Menten equation.
Yeah.
So you need to remember there is a free enzyme. I'll represent free enzyme by EF. Then we have the substrate. And then enzyme and substrate are gonna bind with each other. And substrate, obviously, substrate where substrate bind, Avni?
Yes, sir.
Where substrate bind to the enzyme?
Active site.
Active site, huh? Like this. So this is the active site. Okay.
Yes, sir.
Is there any other site on the enzyme where any molecule, other molecules can bind?
No, sir.
There is allosteric site.
Yes,
Yeah,
sir.
regulatory site. That is also known as the
Yes.
regulatory site. Okay. So
Mm.
you need to remember that. So here we have the ES complex. ES complex. And then this ES complex is going to get converted into product. And the enzyme is going to release the product. Okay. Then enzyme is going to get bind to another substrate. So I can make it like this. So this reaction goes and on and on. And there is another thing, enzymes do not get consumed in the reaction. Enzymes do not get consumed in the reaction. They basically act as a catalyst. Act as a catalyst. Now, we are going to represent here the rate constants for these reactions. This is K1, this is K minus 1, and here we will have the K2. So, what K1 is representing here, Avni?
The equilibrium.
Hmm? Forward rate
Equilibrium.
constant, na? The association constant for the free enzyme and the substrate, na? No?
Mm.
And then
Yes.
K minus 1?
Backward reaction.
Yeah, for the backward reaction, the dissociation
Yes.
of ES complex into E and S. And then
Yes.
what K2 is representing?
Formation of the product.
The conversion of ES complex into E plus P.
And
Huh?
yes.
Yeah. So here we have three reactions. So I will represent this reaction with R1 or rate R1. I'll represent with R2 and I will represent this with R3. So R1 will be equal to how much? Hmm?
K1.
K1, yes. Then
complex.
Not ES complex. These are the substrate now for the forward reaction.
Yes, sir. Yes. EF plus S.
EF into S. Okay. And R2,
R2, K
K
minus
minus
1,
1 into
ES
ES na.
complex.
And then R3,
R3, um,
K2,
K2 into ES complex.
ES. That's correct. That's good. Okay. So you need to remember all of these things if you want to derive the Michaelis-Menten equation. But there are some limitations, or you can say assumptions, because during the derivation of Michaelis-Menten equation, Leonard Michaelis and Menten-Monod, they basically assume some things. Okay. So you need to write down assumptions of Michaelis-Menten equation derivation. First assumption is that the concentration of the enzyme will be much lower than the substrate concentration, because there is a condition that enzyme must get saturated with the substrate. Otherwise, this equation cannot be derived and this equation is not going to be followed. Huh? Second assumption is that concentration of ES complex do not change over time. Uh, to prove this assumption, I need to make this graph. Here we will have the substrate concentration. Not. I will represent two graphs. So one graph is like this. So this is representing, here is the time. As the time passes, you can see the substrate concentration is getting decreased now. Yes or no?
Yes, sir.
Then there we will have the product. Okay. And
Sir.
I'll make another one. This is for ES. So clearly you can see here that the concentration of ES is not changing over the period of time. It
Yes.
is constant now.
Yes, sir.
Yeah. So how the concentration of ES complex is going to remain unchanged over the time? Let me go back. If the rate of formation of ES, what I'm saying, Avni, if the
Yes.
rate of formation of ES becomes equal to the rate of ES complex breakdown, then its concentration is not going to get changed over the time now.
Yes.
And just one more thing, just be here. Yeah. So this is the second assumption, and we are going to derive this Michaelis-Menten equation from this particular assumption. And there is a third assumption that rate of reaction is measured very early in the reaction. Means not late. We are going to measure the rate of the reaction very initially. That's why it is represented by V naught, and it is also called the initial velocity. So these are the three assumptions which are taken into account during the derivation of Michaelis-Menten equation. Is it done?
Yes, sir.
Oh, fine. So, rate of formation of ES needs to be equal to rate of breakdown of ES. So, what is the rate of formation? This one, now,
Yes, sir.
and these are the rates of breakdown of ES, na?
Yes,
Both of them. Okay. So I'll write here K1 into EF into substrate concentration, and that will be equal to K minus 1 into ES plus K2 into ES.
yes,
So I'll take ES common from here. So it will remain like this, K minus 1 plus K2 na, K1 into EF into substrate concentration. What we can do, we can write it like this: ES will be equal to K1 into EF into substrate concentration divided by K minus 1 plus K2. Yeah. Or uh, I can take into the denominator na from here.
yes, sir.
Yeah. I'll write like this: K minus 1 plus K2 upon K1. So what you can see here is basically your Michaelis-Menten constant. Mm, So this is basically Km. I asked you regarding the Km, na? No?
Yes, sir. Yes, sir.
So this is basically Km. K minus 1 plus K2 upon K1. Done? Is it done, Avni?
No, no, sir.
Is it done?
Yes, sir.
Okay. Now, we are going to discuss regarding the Km. But before that, let me remind you the same equation, uh, EF plus S is getting converted into ES. Then ES is getting converted into E plus P, na? Hmm.
Yes, sir.
And rate constants K1, K minus 1, and K2. Hmm. So here you can see association of E plus S and the dissociation of ES into E plus S is a reversible reaction. So from here, you can calculate the association constant, which will be represented like this, K1 upon K minus 1. I'm talking about only this reaction till now, okay? Not about this one.
Yes.
And then the dissociation constant is the invert form of Ka, na?
Yes,
Reciprocal
sir.
form. Yeah. So it will become like this, K minus 1 upon K1. Huh? Now, what is the formula of Km? Can you tell me what Km is representing? Association constant or dissociation constant?
The total,
Hmm?
total calculate कर रहा है.
What is this?
This is association.
So remember that Km represent the dissociation constant. Dissociation constant. Okay.
Yes.
One more thing. The actual velocity or rate of the reaction is not going to be determined by the association or dissociation of ES. Remember that because the actual rate of the reaction is going to be determined by the rate of the conversion of ES into E plus P. No?
Yes, sir.
Did you get my point? Okay.
Hmm.
Yeah. So there are two types of reactions. Some reactions are slow. So I'm talking about the first condition, slow reactions. Okay. In slow reactions, there is a condition that if the rate constant K2 is very much lower than K minus 1. In this case, we can forget about K2. Yes or no?
Yes, sir.
So Km becomes equal to K minus 1 upon K1 na? Because K2 is negligible as compared to K minus 1.
Yes, sir.
So we can leave that.
Yes,
Huh?
yes, sir.
Huh. So here it becomes equal to what?
Association.
Dissociation constant.
Yes, sir.
Okay. In case of fast reactions, if reactions are really fast, in that case, Km will remain like this, K minus 1 plus K2 upon K1.
Yes,
And
sir.
you can see this value is greater than KD, na?
Yes, sir.
Because there is addition of K2, na?
Yes, sir. Yes, sir.
So it is greater than KD. So you can note it down like that. Km can either be equal to KD or greater than that. It can never be less than KD. It can never be less than KD.
Okay.
Yeah.
Yes.
There is another thing. Km value or Km. Km basically what it represent. Km represent the affinity of enzyme towards the substrate. No? And the affinity is reciprocal to the Km value. Let me write like this. Km is inversely proportional to binding affinity. What does it mean, Avni? What does it mean?
So
It
it
means
means
that
that if
if Km is
Km
higher,
value will increase, then binding affinity will decrease.
yes, inverse relation.
Yes.
It means higher Km value, lower binding affinity, lower
Yes.
Km value,
Higher
higher binding affinity. And it is because of what?
KD.
It represents the dissociation constant.
Dissociation constant. Yes, sir. Km.
Yes, that's why there is inverse relation. If Km would have been representing the association constant, then there will be direct relation between the Km and the binding affinity. Okay?
Yes.
Ah. So where we were? ES, EF into S. I can write it down like Km, tha? K minus 1
Yes.
K2 upon K1. I can write it
Yes.
like Km. So Km comes here. Km into ES is equal to EF into S. Hmm. Now, if we want to calculate the total enzyme concentration, then we have to take into account the free enzyme concentration as well as the ES complex. Na? Yes or no?
Yes, sir.
Oh, it got blurred, no? Okay. So from here, we can calculate the free enzyme concentration, which will come like this. ET minus ES. Hmm. I can put this value here in place of EF.
Yes, sir.
Yeah. Km into ES, ET minus ES and into S. Mm, Km into ES. And now we are going to multiply the whole this bracket with S. So it will become like this: ET into S minus ES into S. Is it clear till now?
Yes, sir.
Okay. Now what we are going to do, we know that there is ES and here we also have ES. So we can take it from there to there, okay, on the other side. So it will become like this: Km into ES plus ES into S, and it will be equal to ET into S. ES common from here and will remain like this. That will be equal to ET into. Is it done?
So do
Just a minute. Actually. Just a minute. Am I audible now?
Yes, sir.
Okay, fine. We can move on now.
Yes, sir.
Now, again, I'll write this equation EF plus S into ES. Then we have E plus P. So, we want to calculate the maximum velocity, Vmax or Rmax, maximum rate. Okay. And the actual rate of the reaction is determined by this equation now. This reaction now, this particular reaction. So that will be equal to how much? K2. And one more thing, suppose we have total enzyme concentration and suppose the whole enzyme got bound to substrate, then ET becomes equal to, then ET becomes equal to ES na?
Yes. Yes, sir.
So when the maximum rate of the reaction will be achieved, it means the total enzyme got bound to the substrate. Is it clear?
Yes, sir.
Now come to the same equation. What was ES into Km plus S is equal to ET into S. And one more thing, uh, the initial velocity will be equal to K2 into ES. Yes or no?
Yes, sir.
Because whatever the enzyme got bound to the substrate, that is going to determine the initial velocity, but the maximum velocity is going to be achieved when the total enzyme got bound to the substrate.
Okay. Yes, sir.
Means ET becomes equal to ES. Okay. Uh, if I'm going to multiply this equation on both the sides by K2, what I'm saying?
Yes.
I'll
Yes, sir.
multiply this equation on both sides by K2. Or we can just simplify it first. ES is equal to ET into S divided by Km plus S. I can write it like this now. So I'm going to multiply the both the sides by K2. So it becomes like this, K2 into ES. And here we will have K2 into ET into substrate concentration divided by Km plus substrate concentration. What is this, Avni?
Yes, sir.
What is this?
B not.
Initial velocity.
Yes, sir. B. Yes, sir.
And what is this?
Final velocity. Maximum.
Maximum velocity. So we derived the Michaelis-Menten equation. It becomes like this: V naught is equal to V max into S divided by Km plus S.
Yes, sir.
Now, what I'm going to do, I'll take the initial velocity 50% of Vmax, means half of Vmax. So if I write V naught value as Vmax by 2, Vmax into S upon Km plus S. Vmax is going to are going to cancel each other, no?
Yes, sir.
And there will be multiplication like this. It will come like this on the other side. Km plus S is equal to 2S, na?
Yes,
Or simply Km will be equal to 2S minus.
yes.
It means Km is equal to.
Substrate.
So here comes the definition of Km, which is very frequently asked in many exams and everywhere. Km, what is Km? Km is the substrate concentration at which the initial velocity or initial rate of the reaction is just half of the maximum velocity. Is it clear? Is it?
Yes, sir.
Huh? Okay, now we are going to solve one or two numericals based upon this Michaelis-Menten equation. Okay, suppose I'll give you some values here. Suppose Km is equal to mm, Km is equal to 4S, then what will be the value of V naught in terms of Vmax? Can you calculate it, Avni? This is the Michaelis-Menten equation. So what we are going to do in place of Km, we are going to put 4S, na?
4. Yes, sir.
So it will become like this, Vmax into S upon 5S, and these are going to cancel each other. So it means V naught is Vmax by 5, na? And what is the meaning of this? 20% of Vmax? Yes or no?
Yes,
There will be another question. What will be the rate of reaction when substrate concentration is equal to 2 millimolar. Vmax, and I'm asking regarding the initial. Vmax is equal to 100 micromole per minute, and Km is equal to 2 millimolar. Can you tell me what will be the value of V naught? Can you calculate that? Huh? Hmm?
Yes, sir.
What will be the value of V naught?
Sir, sir, 25.
25. See, it is clear from the question now. Km is equal to, hmm?
Yes, sir.
What was the definition of Km? I told you.
Km is equal to the substrate.
Km is the substrate concentration at
Constant.
which the initial rate of the reaction is just half of the maximum
Maximum
velocity.
velocity.
And here, what is the maximum velocity?
Maximum velocity 100. 50 होगा. So yes, sir.
Answer
50.
will be 50 now.
Yes, sir.
The answer will be 50.
50.
Okay. So we not simply 50. 50 micromole
Yes, sir.
per minute. Okay. Actually, Avani, I have class from 11:30. Okay.
Yes, sir. Yes, sir.
So I think it will be enough for today. Huh?
Yes, sir.
Uh,
Okay, sir.
okay, fine then. Okay, okay,
Thank you, sir.
okay, Bache. Okay. Okay.